Thank you, Chinmoy. I'd like to thank the organizers for, organizing this very nice conference. Okay, so yeah, so as a my association with HRK and Chandan started 20 years ago when I was a PhD student in ISC Bangalore in the physics department. We couldn't have imagined a department of physics without them. We don't have to. And I really look forward to bumping into you in the corridors of the physics department for many, many more years to come. HRK never taught me a course, but Chandan taught us this brilliant course on the physics of disordered systems. So today I shall talk about a disordered system. It's a colloidal suspension approaching kinetic arrest. And even though we couldn't calculate chi4 like we heard earlier today, and I'll tell you why we couldn't, we did extract the length scale out, and I hope Chandan will like it, and I hope HRK also. So I am Ranjini. I'm from the Ramanujan Research Institute in Bangalore, and the work I'm about to describe, it's very hot off the oven. We haven't really had time to really think it through properly, but it's work done mainly by Paramesh, who's a postdoc working in my laboratory. I hope so. You have to tell me that. So, and Devashish, who used to be a PhD student in our group and who is now a postdoc at Dusseldorf, and Sanjay Behera, who's a present PhD student. Okay. Glasses, you've heard enough of it, but then I can't start without, showing you some pictures. So they are all around us, and, they are rather useful, as you can see. You can look out of the window because, your windows are made of glass. This is a metallic glass, this is a molecular glass, helps you store data. And how do you make these materials? You make these materials by taking a molecular liquid and quenching it really, really quickly, reducing the temperature really, really quickly. And structurally, it looks a little bit like this. It's like the traffic in Bangalore. It's all, particles that are jammed together. Experimentally, of course, it's rather hard to do experiments with molecular liquids because, the time scales are rather inaccessible in most cases, and therefore we use a colloidal glass. So we just take colloidal particles, we throw them randomly, and we end up with a disordered material, and Chandan calls it a digital glass, but they do reproduce many, many of the features that, you would expect in a supercooled liquid. And a colloidal glass is opposed to a colloidal crystal, which you can also make where all the particles are very nicely arranged like cannonballs. And just like in a supercooled liquid, where you can approach kinetic arrest by reducing the temperature very fast. In the case of these colloidal glasses, you can actually take a colloidal suspension, increase the volume fraction very fast, and if there's some amount of polydispersity, you end up in a glassy phase. Okay, structurally not a lot happens when you go from a liquid to a glass, but then dynamically a lot happens. You see very dramatic changes. You saw this in the morning. I'm sorry, but you have to see it again. So you find that when you decrease the temperature of a supercooled liquid by a few degrees, like 10 degrees or so, the viscosity can go up by about 13 orders of magnitude, right? And of course, the relaxation time is related to this viscosity. Now, this rise of the viscosity happens in two ways, okay? There is, of course, an Arrhenius way in which the viscosity can rise. There's also a faster than Arrhenius way, and this is called fragile behavior. And this can be explained in terms of an equation that looks like this. This is what very commonly called the Vogel-Fulcher-Taman equation. The inverse, the D is called a fragility parameter. It tells you how much removed you are from true Arrhenius-like behavior, and fragility is defined as 1 over D. This is, of course, the Arrhenius bit that we are not concerned about today. Now, in the case of a colloidal liquid, you can do the same thing. You can actually affect this huge, well, not as huge as in a supercooled liquid, but a rather large increase in the relaxation time or the viscosity by increasing the volume fraction, okay? So basically, decreasing the temperature in a supercooled liquid is equivalent to increasing the volume fraction in a colloidal suspension. And even in that case, you find that the viscosity or the relaxation time rises very much like you saw earlier, and that can be modeled by the again, a Vogel-Fulcher-Taman kind of an equation. And you can also, there have also been work about, soft glasses make strong, soft particles make strong glasses and all that, but then we'll stick to fragile glasses for today. Okay. Colloids, of course, are an entropic system, so you can affect a sequence of phase transitions simply by changing the packing fraction. Okay, so just by changing the packing fraction or the volume fraction, you can go through the sequence of phases. Now, if you add a little bit of polydispersity, size polydispersity into your mixture, then you also get this supercooled liquid and glassy phase. And I refer to this very nice review article that was written a few years earlier. Now, how do you understand fragile glasses? You understand them in terms of dynamical heterogeneities. So here's another traffic analogy. So basically, when you get into a train, there are regions of different, kinds of dynamics. So near the train, near the entrance, for instance, the dynamics is faster. Near the windows, it's kind of intermediate, and away it's pretty much jammed, right? I mean, it's very, very slow dynamics that you see here. So you basically have these, coexisting regions of, cooperative motion that's happening at different speeds. So similarly, something very similar happens in a colloidal glass, where basically if you think of, so if viscosity goes according to this, and of course the activation, EA here is the activation energy, which is dependent on temperature. That increases when the thermodynamic temperature goes down, and you end up with these regions of different, fast-moving regions that are, fast-moving regions of cooperative dynamics that are coexisting with slower-moving regions, and they define a length scale which is called xi het over here. Okay, so basically the more you decrease T, the higher the correlations go, and the fragility of the colloidal glasses, they increase because of the increase of these dynamical heterogeneities, and so the cooperative phenomena are very intricately linked to the heterogeneous dynamics in the system. Now, you heard about 4-point correlation functions this morning. So basically the 4-point correlation function can be extracted from the fluctuations of the 2-point correlation function. And so what the 4-point correlation function really measures is a kind of a correlation volume, the number of particles that are engaged, that are involved in cooperative motion. And as you increase the delay time, you see that there is a peak. And the height of this peak increases. Okay, so as you, for instance, in a supercooled liquid, if you decrease the temperature, the height of the peak is going to increase, and you're going to see the location of the peak is at a point which coincides with a structural relaxation time. And the Ncorr here is the number of particles that are participating in correlated motion, and that is what we are trying to calculate from our experiments. And like you heard in the morning, I mean, in order to calculate this quantity, you need to be able to resolve your dynamics both in space and time. For us, I mean, we are looking at really, really tiny particles, so it's very hard for us to track their motion and look at their mean square displacements under a camera, under a microscope, and therefore we have to resort to something else, and so therefore we calculate a 3-point dynamic susceptibility. And you heard about all the experiments about granular media this morning. There are also beautiful experiments on hard sphere colloids where a non-Gaussianity parameter has been calculated, and you see exactly how it changes close to the glass transition temperature. Now, like I told you, we are working on a nanocolloidal suspension, so the particles are really, really tiny, very hard to track, okay, and therefore we calculate a 3-point dynamic susceptibility, which for hard spheres goes like this. And this is our 3-point dynamic susceptibility, and it basically measures the nonlinear response of the 4-point susceptibility. It sets a lower bound to the chi4, and it is basically the response of the 2-point correlation function to a change in the control parameter. So now I'll tell you the material with which we made our colloidal glass. So we used a clay suspension So this material that we used, it's a designer clay called Laponite. So it is an inorganic molecule that looks like this, and it really looks like this. So as you heard this morning, this is a silicon. It has silica, it has magnesia, and so on. But then it really looks like this. It is a disc-shaped molecule whose diameter is about 25 to 30 nanometer, and which is about 1 nanometer across. Now, when you take such a particle and you release it in water, then sodium ions, positively charged sodium ions, diffuse out into the water. So you have one particle that is surrounded by a very large debye layer. And when you have many of these particles in water, you have a very strong repulsion between these debye layers. And this happens gradually because of a buildup of electrostatic interactions that I cannot really discuss right now, but I'm happy to talk about it later. But then as a result of this, this material ages, okay? And eventually you're going to form a soft Wigner kind of a glass. And I can just tell you how we make the suspension. So Laponite is like a powder. It's a white powder. We just disperse a little bit, about say a volume fraction of 1% in water. So initially, and then you stir it a lot, and then initially it's like a liquid that's about 10 times more viscous than water. But then you just seal your bottle, make sure nobody's touching it, come back after a day, and it's become a glass. So it can actually support its own weight. So you can actually turn your vial over and it behaves like a solid. Okay. So this is our Laponite RD, is a particular grade of Laponite only at 3 weight%, which is basically, this is the volume fraction here is about 1.8% after 2 days of preparation, and we've done nothing to it. The reason why it transformed from a liquid to a solid was because of a gradual buildup of electrostatic interactions A and a gradual process of tactoid exfoliation. So these are particles that are in stacks, and eventually the stacks all basically they fall apart into individual particles, and this kind of exposes more debye layers, and the electrostatic interactions increase a lot, and this gives rise to a Wigner kind of a glassy material here. So what do you do when you see something that whose viscoelasticity has changed significantly? You put it in a rheometer. And in this case, we put it in a cone and plate rheometer, where you can do 2 things. You put your material on the rheometer bottom plate, you can change the amplitude and you can change the frequency. And just by applying very small amplitudes and frequencies, you find that the elastic modulus, which is the energy stored in the material, written as G prime, and the viscous modulus, which is G double prime, it just evolves spontaneously with time. Okay. You can see this is about, I think, a few hours, and the elastic modulus, which is the red line here, has gone up by a factor of almost, well, by about 3 decades. Okay. So another, very popular experiment to look at the soft glassiness of a material, of course, is to do a frequency response. You keep the amplitude constant, you change the frequency, and sure enough, we see the signature of a soft glass here. You see that over this range of frequencies, which is rather large, you can't do very much more with a rheometer. So now the G prime has become black, I'm sorry about that. So it is frequency independent, and it's way, way larger than the G double prime, the viscous modulus, which is only very weakly frequency dependent. Okay, the other test that we normally do is you change the strain. And here you see this sudden peak in the viscous dissipation, which is basically, it signifies an yielding process, which you also heard about this morning. But anyway, so here's how we make our colloidal suspension then, our glassy suspension. So we just take the powder, throw it in water, and just wait for it to evolve. And so basically, once you stop the sample, it just does. This is at a particular age. Yes. So yeah. So here also you have to take certain precautions when you do these experiments, because your sample is aging as you're doing the experiment. So they have to be done rather fast. So yeah. So we basically, you'll find a parameter called a waiting time here, T sub W, and that's basically the time that has passed since you stopped stirring the sample and you put it into the container, or into the experimental geometry, and that is, besides the phi, which is the volume fraction, TW, the waiting time, is one of the control parameters of this experiment that I'm about to describe to you here. And so basically, you just take a fresh sample, you load it into your experimental cell. So initially it's, well, more viscous than elastic, but then, it evolves, it becomes very, very elastic, very, very glassy. And during this time, we have calculated our correlation function, and from there, we've tried to extract a length scale. So the experiment that we have used here is a dynamic light scattering experiment. Now, Laponite is a very poor scatterer of light, and because here we want to calculate higher order correlation functions, what we've really looked at is the probe dynamics in an underlying aging Laponite medium. So the probes that we used here are polystyrene particles, which are very strong scatterers of light. They are in very, very minute quantities, so that, just to ensure that the Q into the interparticle distance is much, much larger than 1, and therefore you're in the, and of course the particles that we've used are also much smaller than the wavelength of light, so you're in the single scattering limit. And we basically looked at the evolution of the dynamics of these probe particles, and we have indirectly basically analyzed the data to understand what the underlying medium is doing. Okay? So for those of you who do not know dynamic light scattering, it's a very simple experiment. So this is the sample that we put here. We blast it with a laser, the sample scatters light, and the light is collected by a photomultiplier tube, and for a very, the simplest system that you have, which is a dilute suspension of monodispersed spheres, is going to look like this. Okay, it's noisy. So what do you do with noisy data? You correlate it. So then you take the output of the photomultiplier tube, and you send it to a correlator, and and there's a computer which can compute this this intensity autocorrelation function. Now, you can use that intensity autocorrelation function to come up with an electric field autocorrelation function, okay, which is our 2-point correlation function over here. And if it's a very simple case of just, monodisperse hard sphere diffusing around in a liquid, you can use all these relations and actually extract the size of this particle. Now, all materials are not monodisperse, neither are they freely diffusing. Suppose you have polydispersed suspensions, then this is basically the weight factor which you can extract from your dynamic light scattering data to calculate the size distribution of the particles. Okay. Now getting back to our experiment with the Laponite, so here I'm talking about our data that we got by putting a very small volume fraction, about 10 to the power minus 5 in a Laponite suspension. So you take a fresh clay suspension, okay, you put a very, very minute volume fraction of probes in it, which well, they are randomly distributed, and you know that these scatter much, much more strongly than the underlying Laponite medium, and you look at the scattering from these particles and you calculate the 2-point correlation function, which goes like this, and this is our data. So here are the TWs, like I told you, were the aging times, which is how long you waited after you prepared the suspension, because remember, the suspension spontaneously evolves in time. The elasticity and the viscosity both evolve because of an evolution of the underlying dynamics. And there are two interesting features that you see here. Maybe, there's a lot of data, we've shifted them for better visibility and so on and so forth. But two things here is that these fit very well to two-step relaxation functions. There is you heard about the jiggling motion in a cage this morning. And the first part is basically, you can attribute it to the jiggling motion, and the second part, which is this can be attributed to the slow structural relaxation time, and that throws up a time scale which is commonly called the alpha relaxation time, tau WW, which is what we are interested in this work. And here's how we've calculated. We've used a gamma function, an Euler gamma function, to calculate an average value of this slow structural relaxation time. Now, we have lots of data at lots of different aging times and lots of different volume fractions. So then you can always plot these slow relaxation times versus these control parameters. So control parameters here is the time since preparation or the waiting time, I'll not call it the aging time, and the volume fraction. And you see that, well, this is the data for the TWW that we got versus the waiting time. And you see that at least, well, the range is not much, but that is really that's a limitation of the experiment. But then you can fit your data to a Vogel-Fulcher kind of an equation. And when you change the volume, so when volume is your control parameter, you see that the same thing happens, that the slow relaxation time, it evolves with the volume fraction following a Vogel-Fulcher-Taman kind of an equation. Again, the ranges are not much, but that's really nothing. We can't do much about it because the glass phase of Laponite is very limited. If you go to lower concentrations, lower volume fractions, you have a liquid, okay? If you go to higher volume fractions, you end up in a nematic phase, okay? So therefore, we really don't have a lot of wiggle room over here. So now one interesting parameter that I didn't tell you about is this stretching exponent beta, okay? Now basically for free diffusion, you'd expect beta to be close to 1. But then in our case, you know, where there is some amount of heterogeneous dynamics, beta reduces from 1, okay? So this is again versus the beta, which was the stretching exponent that I just showed you, plotted versus the waiting time. And you find that initially beta is close to 1, but then later on it decreases rather quickly. And then you can also, you can use that Kohlrausch-William-Watts kind of a function that I just told you about. You can invert it and you can find a size distribution like I showed you in an earlier slide. And this is exactly what we've done here. So this is the earliest, well, one of the earlier data that we took. And you can see this is after 1.53 hours of preparation of the sample. This data is, so this is a relaxation time distribution. It is narrow and it is peaked at 1, okay? But as the age of the suspension increases, you can see that this distribution becomes wider and then the peak also shifts to the right, okay? So this is how we've calculated the distribution function. Now, how do we calculate the 3-point correlation functions? We need to parameterize the Kohlrausch-William-Watts equation that I just showed you, because we need to see how the two-point correlation function changes with respect to the control parameters here, which are the aging time and the volume fraction. And so that will be the data on the left. So this data is basically the 2-point correlation function that I just told you. The fits are a little different. So what we've done here is that, so we had the TWW, remember, the slow structural relaxation time. So we've just basically parameterized that part with the Vogel-Fulcher-Taman equation that I just showed you fits very well to the data when we used our, well, the earlier fitting that we did. So we've just parameterized the equation and the red lines that you see here are the fits. And what we've extracted from here are really the, well, the A and the beta, but then, and then we've done the same thing for the, we've done the same thing for the figure C here, which is basically the 2-point correlation function where we had the volume fraction as the control parameter, where we've parameterized the slow relaxation time by this quantity, which again we know fit very well to the data. And using this also, okay, so these are the fits to the data. We fit the data with polynomial functions and we calculate chi-t by basically taking the derivatives at infinitesimally small intervals of tw and phi using Mathematica, okay? So these are our two correlation functions, and that's figure B here for the case where the control parameter is the waiting time, and figure D here where the control parameter is the volume fraction. And in both cases you see that as the control parameter increases, you can see that not only are the heights of the peak increasing, okay, which basically tells you that the size of the correlated regions are increasing in your sample, but it also shifts to higher times, which means that your dynamics are getting slower and slower. Now with this we want to calculate an Ncorr, okay, the size of a region of correlated motion. Now just like chi4 shows a peak, you can also show that this 3-point correlation function also shows a peak. And that is what we have to extract from our data, and we know that this Ncorr, it is proportional to the height of the peaks that I just showed you in the last plots, B and D. So over here on the left side, you see the data where the waiting time is the control parameter, and these are the peak heights, and these are the Ncorrs that we've calculated from the data. So this is the expression for the Ncorr when you know this, which we calculated in the previous slide. So to find Ncorr, you need to suitably normalize the data. So how have we normalized the data? In this case, we've normalized it to that waiting time where we found that the size distribution had a very sharp peak. What that means is that your relaxing regions, okay, they were not engaged in any cooperative motion, and that basically it was almost very close to free diffusion, and you had a single relaxation time in your sample. On the right side here, you see what we get when we change the volume fraction of the suspension. So this is, so I've just, to make things a little easy to understand, I've just plotted two ages here. So the black points that you see here are for a freshly prepared sample. And that here are our, so we've calculated the Ncorr here, and you can see that it increases much more slowly than the increase at a higher waiting time when your system is way more glassy. And here again we have also, so basically Ncorr is equal to 1 has been, we've basically force fitted that to an earlier data where the beta, the stretching exponent, is equal to 1. So we took a sample where the stretching exponent was equal to 1, as well as the our size distribution function was sharply peaked, and so that is our proportionality factor here, which I haven't written. Okay, so then we did something else, and we kind of got the idea for this by looking at a paper on supercooled liquids that came out in 2007 by Dalle Ferrer et al. On supercooled liquids, where they did nonlinear dielectric spectroscopy. But here we've just taken our own Ncorr data and we've plotted it versus the slow relaxation time, and we've normalized it by a glass transition time, which is, well, I mean, the time at which the our suspension enters the non-ergodic state, and this is what we see. So the black symbol that you see here, these are our calculations for the Ncorr, okay, the region, the size of the regions of the correlated dynamics, and the red symbol that you see here, this is for the beta, which is the stretching exponent, which basically is a measure of the heterogeneous dynamics. And on the right side, you have the same thing, but at a different volume fraction, okay? So, and you see the same thing. So basically, the Ncorr in both these cases, I mean, the volume fractions are not very different, but they are, well, I mean, I think they're different by a factor of 2. You see that the Ncorr, it initially increases rather rapidly, and after that it slows down. It slows down close to 1, okay? And probably because as you're coming closer to the non-ergodicity point, I mean, it's getting more and more difficult to move because of the activated dynamics that are becoming slower and slower. So just to sum up, so the Ncorr is evolving faster initially in both these concentrations that we've looked at, before eventually slowing down. The beta decreases simultaneously. So beta was the stretching exponent, which was basically a measure of the width of the distribution of the timescales that we earlier measured. And this implies the simultaneous increasing heterogeneity of the dynamics. And both these features result in the fragile supercooled liquid-like dynamics of these Laponite suspensions that we are using here. So just to compare the data that I just showed you, we came across this, this very, very rigorous paper with a lot of data that was written in 2017, where they used dielectric spectroscopy. So what they basically measured was chi-T, okay? And so these are the, they have, like I said, I mean, it's a very, very complete set of data. And here they have calculated Ncorr, and we have actually followed their prescription to calculate the Ncorr that I just showed you. And they plotted it versus the alpha relaxation time, normalized that by the microscopic relaxation time, which was tau g, like I just showed you in our plots, and they see the same thing. So this is normalized, they basically overlapped all the data. So here you see, I mean, this is for a range of supercooled liquids. They find that Ncorr, initially it increases as a power law, and after that it shows a logarithmic growth close to the, well, I mean, to the point of non-ergodicity. I have a lot of time left, but I'm done for a change. so I'll just sum up what we saw. So basically we see that Laponite, we have done earlier experiments where we showed that, Laponite has, Laponite suspensions show fragile supercooled liquid, but, we've tried this time to basically quantify it a little bit more. And we have done that in terms of a 3-point dynamic susceptibility. This 3-point dynamic susceptibility, like you just saw, exhibits a peak. And the peak height grows with increasing sample age and volume fraction, which are our two control parameters. We also show here that the sizes of the dynamical heterogeneities, the cooperative rearranging regions, which we quantify in terms of Ncorr, they increase with increasing sample aging times and volume fractions, and the widths of the distribution of the these regions of correlate, of the dynamic. The width of the time scales of this time scale distribution also increases simultaneously. We also showed that the evolution of the sizes of these dynamic heterogeneities is initially very fast, and after that there is a slowdown very close to the non-ergodic transition, and this is very reminiscent to several observations in fragile supercooled liquids where, of course, different methods were used. Like in this case, you had the measurement was of the nonlinear dielectric response. And this is basically, we are hoping to use this to push our case of, basically pushing Laponite as a prospective candidate for a model glass former.
This 3-point correlation that you are calculating, is it not similar to the correlation function that Reichman and others talked about? Now, for that kind of correlation functions, Sriram and his student did some dynamics.
They have, yes.
And have you compared with that kind of power law?
No, no.
Very nice. So I have a few questions. If you can come back on the last results. Yes, here. So here, if you overplot the different curves for the different phase, in the spirit that they compare, there are different liquids. Do they superpose, or it's not so good?
So because we didn't have time. I mean, obviously that's something that we'd really like to check. Yes, so in that case, basically we normalize by the phi infinity, which is where, you expect that, the dynamic. Yeah, so like I said, hot off the oven. So, I mean, this is rather incomplete, and yes, that is something that we have to do.
And then a second question in the same spirit. I mean, in some sense, here you have the two behaviors, the fast growing and then the saturation, but on 1, 2, 3, on four decades into alpha.
I'm sorry?
In 4 decades into alpha, right?
Yes, yes.
So when you look at the true liquids, it is not 4, it's like...
So that's because of this normalization by the...
I use just tau G instead of tau 0. Okay, okay.
Yeah.
Okay.
So I had two questions. So I mean, in terms of the results that you present, I guess one thing that at least I'm surprised by is the fact that there's a finite aging time at which you seem to have divergence of the relaxation times. That I guess that's sort of not the standard aging.
I mean, it's not finite within the length scale of an experiment. I mean, these are all fits. I mean, you're really sitting in a rather, ergodic regime, and everything is based on fits. It's all extrapolations.
Sure, but still, I guess...
So in this case, for instance, our divergence would happen at 30 hours. That's our Vogel time, if you will.
Yeah, no, I'm saying in sort of the aging literature, and maybe Walter can say more, but you expect something like a linear or a power law.
No, it doesn't well. Digital glass, right?
Clearly
you don't see power laws here. Not very much.
Yeah. Okay. The other, sorry. Yeah, maybe I would like to come back to this to the extent this time. The other question I had is, I mean, when you are, I guess, looking at a very dilute system.
Yes.
And probably, I don't know if the densities are varying. I mean, the suspension concentrations are not changing, I suppose, but...
for a given experiment, I mean, we have the concentration in a series of experiments.
True, in a series of experiments.
Right.
But no, the this relation between the chi's and the derivatives of the correlators will look somewhat different, I think, for gel-like systems rather than.
I'm guessing what we used here was really for hard spheres. And we basically calculated the prefactors according to a model for hard spheres.
Okay. All right.
Done by Lunkenheimer and Colloidal, where they fit a modified KWW, where you take the relaxation time itself dependent on time, and it fits quite well. I mean, I have also seen from the solution of MCT equations, that kind of form fits much better, you know, to the data, the aging data.
So, you know, I'll find out about this from you.
I have two questions. What is your guess about the ultimate fate of beta?
Well, I mean, we couldn't go beyond this.
I understand.
So I really don't know how to answer that. Guess, I mean, it seems to saturate. I mean, does it? I mean, I don't know.
It's not saturating.
Yeah, well, it's on a log scale and it's not changing very much. So, you know, okay, so the limitation that we had here in this experiment was that, like I said, you know, so we are fitting a correlation function. To fit a correlation function, you need to, you know, fit the baseline to something. So in this case, we need to fit it to 0. So the data that we have here, this is really all in the, you know, this is ergodic. I mean, it's of course, you know, stretching, it's getting longer and longer, but then you're using DLS, which doesn't do so well. And also when you're doing the experiment, you don't want the sample to age, which is why we couldn't resolve, you know, in space, because you cannot look at different angles simultaneously and, you know, expect to compare. So yeah, I mean, I will put that to a limitation and no comments.
My second question, perhaps I missed it, but the formula that you are using to connect the derivative of f with the Ncorr applies to equilibrium systems. Now,
okay.
now you are making a leap of hope, of faith.
I mean, in our data can be thought to be ergodic, like I just said.
But wait.
But I agree, the underlying medium is aging, yes.
So, I mean, if your aging is weak, then maybe it's working. But I mean, we did some numerics on out of equilibrium dynamics, and then we saw that the shape of the correlation function is very different from the stuff that you get in equilibrium. And so since you also see that the things are, that the beta is evolving with the waiting time, so things might be a bit more complicated or more interesting, let's say, than one would naively expect. So I mean, I cannot say anything because I have no theory for the out of equilibrium aging thing. But it might be useful to be careful on that.
Okay.
Yeah, to bounce on this remark, have you tried to see if the Ncorr that you extract from the derivative with respect to TW around a certain phi is equal to the one that you extract when you derive with respect to phi close to this TW, where you took your and it's essentially the same.
It's same, yeah. I mean,
that's a good.
Go from 1 to 30 and.
Yeah, that's a pretty good check.
We have done that, yes.
Yeah,
but that's a very interesting point, and we keep it in mind.
Any more questions or comments? Your full chair TW is like 35 hours, right? You're supposed to divert. Your relaxation time is supposed to divert if you waited for 35.
Okay, that is, yeah. So, you know, that's there again, that's an arbitrary, you know, 100 seconds kind of. So you're assuming that, you know, when it's, the relaxation time becomes 100 seconds when it is 35 hours. Oh, you mean in the, yeah, that diverges, correct, yes.
So, I mean, 35 hours is not that long. So I mean, why can't you wait for 35 hours and see what happens?
You can't, because by then, see, because you have a finite, so the way you're measuring it is, so you're calculating a correlation function. You also have to average the data to ensure good statistics. You need the data to completely decay. You need the correlations to completely decay within the time scale of your experiments. And I mean, this is not a multispeckle experiment. This is a dynamic light scattering experiment. Your total averaging time can't be much. So all you can do is, you don't have a lot of wiggle room. So, you take some data and then you make this wild extrapolation and you claim that, this is the aging time. But yeah.
Okay. And this time scale that you get from the peak of that chi3 and the alpha relaxation time that you get.
They are similar, milliseconds in this case.
So, I mean, I'm looking at the numbers that you have on this graph. It's sort of going from, I mean, it's the n is going from 1 to 10 roughly, and that's...
Not much, yes.
Well, depends. Depends on who you ask. But she said it, I didn't say it.
So these are, I mean, if you look at a single part, yeah.
Right. No, I just wanted to know, have you compared it with other systems where...
Just told you the answer.
That's the...
Yeah, we were happy, let me just say that. We haven't done all that yet. And we don't have a lot of, the dynamic range is rather poor. So should we fit a power law is the question. That's always the case for colloidal glasses, yes.
Okay, thanks Ranjini, 1 second.